Hello, everyone, and welcome to the penultimate day of Architizers Future Fest. To everyone who's attended our previous presentations this week, welcome back. And if this is your first event, thank you for joining us. Future Fest has been a 3-week-long event featuring a range of A+Award-winning architects from around the world, forming a vibrant celebration of architectural innovation. It's also our way of warming up for the 11th annual A+ Awards, which launched this October. Stay tuned for more details on that later on. For everyone who doesn't know me, my name is Hannah Finiak, and I'm the architecture editor at Architizer. Today, I'm delighted to have the opportunity to chat with Yasemin Kologlu, who's the principal and sustainable design and climate action leader at Skidmore, Owings and Merrill, which most of you probably know as SOM. If you'd like to learn more about Future Fest or to see our full schedule of talks, you can go to architizer.com and click on the very top article. Here we list the names, the times, the dates of every talk that we've had in the past 3 weeks, along with a little description of the kinds of content that you can expect from that hour-long recording. Through that article, you're able to click register, and that'll give you access to the recordings of the previous talks. So just while we're waiting for the room to fill up, I want to encourage everyone to say hello in the chat box that you'll find on the right-hand side of your screen, and let us know where you're from or where you're tuning in from. While we do that, I'm going to share a few pointers about using the platform, just again, as we wait for everyone to enter the room. So firstly, if you are having technical difficulties with the stream, you can click on the help icon in the bottom left-hand corner of your screen. And from there, you'll see a few options for improving your picture, the sound quality, and so on. More often than not, we find that issues with sound and picture quality can be resolved simply by refreshing your browser, so maybe try that first. Secondly, it's worth noting that there will also be a recorded version of the talk, which will be sent to your email shortly afterwards, so you can catch up on anything that you missed. You can also feel free to forward that email to colleagues and friends after the event so that they can register and watch the talk as well. Thirdly, we encourage you to use the chat box to discuss and comment on the presentation, but if you have a question that you'd like to ask Yasemin at any time, please head over to the questions tab, which you'll find at the bottom right-hand corner of your screen, just next to the chat icon. If you see a question from someone else in that section, you can also upvote it, and I'm going to try to pick from the most popular questions a little later on. Finally, I want to draw your attention to the React button, which you'll find in the central bar at the bottom of the screen. From there, you can select, there's a small handful of emojis that kind of can show your engagement with what Yasemin's saying. All right. Thanks, everyone. We've got that one down pat. So now, allow me to introduce today's speaker, Yasemin Kologlu. A recognized leader in sustainable design and construction, Yasemin plays a central role in SOM's efforts to transform architectural practice and lead the building industry's response to the climate crisis. She adopts a forward-thinking and holistic approach to design that integrates well-being, environmental design, and technology. She advocates for equality, diversity, and innovation in design. Yasemin joined the firm in 2004 and has worked at SOM's London and New York studios. Her portfolio of completed projects is diverse, spanning from innovative headquarters and near net zero offices to net zero carbon residential and mixed-use developments. Among her most notable works is Urban Sequoia, a radical proposal for a carbon sequester and high-rise, as well as the United States Census Bureau headquarters in Maryland, the JTI headquarters, and the United Nations campus in Geneva, and as well as the Carla Tournay in Gothenburg, the tallest residential tower in Scandinavia. Thank you so much, Yasemin, for joining us today. And without further ado, I'll pass the mic off to you.
Thank you. I hope you're able to hear me, see me. Perfect, great. Thank you for that fantastic introduction, Hannah. I think let's start with maybe a little bit of the basics here. You know, Urban Sequoia is an idea that we developed actually in order to think about maybe come up with a prototype that could take our building industry or built environment from emitting 40% of global carbon to actually absorbing, sequestering 40% of global carbon. So we challenge ourselves, and can we bring technologies, materials from other industries or in development into a building, into the built environment? So what I'm going to show you today is talk a bit more in detail about what the challenge was, what some of these ideas were, and what kind of opportunities we found along the way. And hopefully at the end also we'll have time for your questions as well. So to start with, I think many of us probably on this call are familiar with that. I think the climate change is already throwing the world system out of balance. So we're seeing it, and being in the US at the moment, we're seeing some of the biggest storms coming our way, and the storms actually becoming more and more frequent. We're seeing other challenges on the West Coast, in other parts of the world. So this is real and is happening. And it was quite eye-opening for us when we thought about where are we with climate change? Where are we with temperature increases? And the main cause of this temperature increase resulting in climate change is actually the embodied carbon, is the carbon emissions and the greenhouse gas emissions. And currently we have our temperatures have risen globally 1.1 degrees Celsius. And they're anticipated to rise another 2.3 degrees Celsius by the end of the century if we're not taking active precautions and measures. And knowing that a big chunk of this comes from the built environment made us ask ourselves, what can we do to bring that down to 1.5 degrees at the end of the century to limit the impact and the change that we might see in our planet? And I always say, I was born into an amazing world, and I'm hoping to leave an amazing world for my son as well. And many of us probably share similar feelings on this call as well. So there's a greater incentive for all of us as designers to try to find solutions here. And maybe the other challenge we had was, we think about, is the density right? Is the density the answer to our problems? Could it be a solution, or could it be the problem? And I think we are saying that the density is actually not going anywhere, because our population globally is going to increase 2.1 billion by 2050. It's a huge, huge, huge number. But also on the chart on the right side, you're seeing that our CO2, carbon emissions, are directly almost following the same pattern. So as we increase our population, our emissions also increase along with that too. So we are trying to decouple those, and the built environment has a big role to play here. And the cities around cities around the world are growing. And we are going to need twice as much as built area as we have today by 2060. This means that demand on cities will grow, demands on the planet will grow on energy, and the emissions are likely to grow unless we find radical forms of reduction and absorption from the atmosphere. And in this equation, the cities actually account for 70% of our global carbon emissions every year. And it's huge, 70%. And it's not just buildings, of course, but it's the industry around, it's the transportation around, and etc. But also we should note that cities have the potential to be the best performers in terms of carbon emissions if we do them right. So our exercise today, our prototype today, is going to try to untangle some of those things that we're talking about. So we came up with this proposal, and we said to ourselves that net zero architecture, which is many of us are working towards, that is just not enough. That's still a reduction. But can we change the way we think about buildings, and can we let the buildings absorb carbon, is what we asked ourselves. In other words, what if the buildings acted like trees? Can we really imagine buildings literally, physically absorbing, breathing air and absorbing carbon from the atmosphere? And this took us to our proposal that I'm going to talk about today. The proposal is Urban Sequoia, and we're actually looking at a prototype that absorbs carbon directly from the atmosphere by using innovative technologies, innovative systems that exist already, some in our industry, some outside of our industry, and also innovative materials. So here, I'm going to take a moment, and Hannah, if you could show us the video here for a moment. Our video gives a good summary of our thinking and what went into this, and then we'll continue the presentation right after that. Perfect. Thank you, Hannah. So I hope that gave a good introduction to what we'll be talking about in more detail here. But the idea was, again, what can we do to create a building, to create a prototype and a built environment that absorbs carbon? And to do so would require us thinking a little bit outside the box. It would require us to leveraging existing technologies and emerging solutions and materials that exist potentially in the built environment, but also outside of our industry. They may exist in research, they may also exist in other industries such as energy creation and development. And also, while we looked at these technologies, we wanted to create a prototype that was applicable to not just a high rise, but also mid-rise and a low rise. And we started with a high rise. So what you're going to be seeing today is a high rise because it's the most challenging of the typologies in terms of creating efficiency, in terms of creating optimizing the energy use, optimizing the carbon emissions and reducing them. So we took the hardest of all of them in our mind to try to push the limits and see how far can we go here. That said, though, we didn't limit ourselves to one typology. We looked at a small house, we looked at a mid-rise, low-rise, and a high-rise together. And we think that this type of transferability of the system is important because these are key components of our cities. So today we're not going to be proposing that all cities has to become high-rises. In fact, exactly the opposite. We're saying that different sizes, different buildings, different uses must adopt some of these strategies, could adopt some of these strategies to find the solution to our problem. So going into urban Sequoia in more detail now, what we're proposing here is actually we are looking at 3 different types of innovation coming into the built environment. The first one is biomaterials. So these are materials that are innovative in the way that they work. Either they absorb carbon from the atmosphere in the way they're generated, or they might continue to absorb carbon from the atmosphere. The second one is the nature-based solutions. So these are systems that could use photosynthesis, which is a natural phenomena that our trees use. For example, systems like microalgae systems that exist in other farm format right now, not used in buildings, but they're farms that we use for microalgae production, for example. And they're also a great source of biofuel. And the last one is technological advancements, such as direct air capture technologies. So these are machines that actually can absorb carbon from the atmosphere directly and actually use them elsewhere in different industries to use it as a commodity almost. And I'm gonna explain in a little bit more detail. So as part of this effort, before we even got to these innovative systems, we looked at what can we do to optimize our buildings first. So just simply by using modularity of our systems and using prefabricated systems, we are able to reduce the total carbon emission of a building about 30%. This is already huge. And the point we were making is that we have to reduce so much as we can first. And then we have to use these innovative technologies to further enhance the performance, the absorption of the building. And that's the path that these buildings will need to take. And then the next step was for us to actually look at the holistic integration of components. You know, our buildings are often designed in such a way that they're additive. So we'll look at the structure, then the MEP, then the floor finish, and the interior design. And we were thinking, can we approach it from a slightly different angle? Can we look at an integration of all systems? And this will result in another 30% of reduction in the building systems, in the energy use and carbon emissions altogether. And what this could mean actually is that if we look at the overall picture, so we are able to potentially reduce the carbon emissions of these buildings by 95% upfront. And then over 60 years of their lifespan, not only they're not emitting further carbon, but they're actually absorbing 350% more than they would have emitted as a typical building. This is huge. Can you imagine a world where actually buildings act like trees? They're actually not part of the problem, but they're part of the solution to our climate, to our greenhouse gas emissions. And this was quite interesting to think about as a single building. But we also realized that the potential of this is much greater when we think about it as a whole group of buildings, network of structures, a city network, and maybe even a global network where buildings talk to each other. These networks work with each other and they complement each other. So, and by doing so, we could actually use some of the carbon saved elsewhere, the microalgae produced elsewhere, and create a synergy between buildings and the built environment to further optimize the carbon emissions, the carbon reduction and carbon absorption of the built environment. So coming back to how do we do this, you'll see that we highlighted a couple of ideas here. So the algae and biomass, the biomaterials, as well as the direct air capture from the direct carbon capture, basically, from the atmosphere. And let's go into them a little bit more. What we already spoke about, the biomaterials, nature-based solutions that work with natural phenomena, and technological solutions that can invent new technologies to absorb carbon. So starting with the biomaterials first. Interestingly, we actually have some of these materials already developed. And currently we are working, for example, with Prometheus materials on what we call the Biobrick. And there are other similar technologies, also materials that exist too. But this is a great example. It's an example where aggregate, algae, and a water solution is put together to form the material. So a brick can be produced with these three simple ingredients. And as part of this formation, it will absorb carbon from the atmosphere. And this is what it might look like. And it could be in different forms. It's a cast material. It has great properties. And quite an innovative material that can help us reduce the carbon emissions for a building. And what's impressive about this is it uses, again, the simple materials that we're talking about here. But all the materials used in this, all the substances used in this is food grade. So these are actually, you can see that it's a safe material that are it's actually the kids of one of the scientists that we're working with in the research institute that is casting these materials to showcase it. And the benefit of it, because also it basically uses sand, a hydrogel, and algae. And you can imagine that many of these exist in many places around the world. So we're not thinking that this is a solution for only Western world or the Northern Hemisphere or the Southern Hemisphere, but this is actually a solution that could be applicable to many locations, remote or not, city or rural in the globe as a broad scale. And what this does is for example, it's not the only material of such, but I wanted to highlight one of them today. For example, Biocrete is another one we talk about. Biobrick is the one we talked about, and the bioplastic, for example. And all of these materials could absorb carbon from the atmosphere, become part of our solution here. And can we advocate or explore the wider use of some of these materials to go to that carbon sinking strategy that I talked about in the lifespan of the building? Can our structures, our partitions, our walls be made of this type of materials? Can you imagine, like if let's imagine that my apartment, for example, was actually absorbing carbon from the atmosphere as I'm living in it. I mean, what a great story to tell in a way, but what a great cause also for a building to perform as. And the great thing about some of these materials is also that they're often produced and cast in and they can come in different shapes. They're often coming as modular elements, which further enhances our idea of the modularity that I talked about in the beginning. Now I'm going to pivot to a different system, to the nature-based solutions that we talked about. So when coupled with technological advancement, also nature-based solutions that benefit from photosynthesis, for example, of absorbing carbon directly from the atmosphere by the phenomena of photosynthesis, represent great opportunities for us as well. In this scenario, this is actually a built facade that was developed in Germany that uses the algae, sunlight, and as a result, the two together is producing more microalgae in the system and absorbing carbon from the atmosphere. Fairly simple, actually, and you might have seen it in also farm formats. So these are pictures of some of the microalgae farms that exist around the world. And it's often used as a biofuel, biomass, biomaterial to complement and replace some of the fossil fuels, for example, or reduce the demand on bioelements that we have in our agricultural fields. And it's fairly simple again. It's a clean source of energy. It's relying on photosynthesis, producing algae, using water and direct sunlight to produce this. So can we think of a world where parts of our buildings could actually adopt these. And our facades in a high-rise or a low-rise get a lot of sunlight usually, and we work hard to mitigate that, to reduce that. Instead, in this scenario, can we use that to our benefit? Can we locate some of these elements there, so to allow them to produce and perform photosynthesis and produce potentially biofuel, biomass in this scenario? And we're suggesting that potentially parts of our building's facade could do so. It can be facade integrated system, just like the one that we showed in the previous images. And it can actually produce biomass, biofuel, that could then be used as a source of energy, for example, as a source of heating, electricity production potentially, but also as a bioprotein that we might be able to use in our other industries as well. So it has a global benefits altogether. And the way it actually, so this is the previous system that I showed you. It's could we produce biomass on the building, biofuel on the building, and let it fuel the building systems, so we don't rely on fossil fuel, we don't rely on electricity, and actually, and any excess that we might have connected to a network of buildings in the city to use it elsewhere in potentially power generation, in food industries, jet fuels, heating and cooling, or manufacturing other materials from some of these. And this is actually a built example of this type of technology. It's a built building, and you can see the facade has microalgae actually in it. To give you an example of what this could be like, a solar leaf building in Hamburg that we were exploring and understanding more as we develop some of these strategies. So pivoting one more time. Now I'm going to talk a little bit more about the direct air capture and the technological advancements maybe. So in this scenario, it's actually what you see in the background here. You're probably seeing these machineries that are modular and sitting next to each other. And this is very similar to maybe, if you recall, photovoltaic farms that were producing energy in the open fields. So direct air capture machines that absorb carbon from the atmosphere are working right now in a similar fashion. They exist in areas with in a farm format like the picture that you're seeing here. And what they do is actually the carbon, the air directly goes into the machine. It's absorbed by a filter. And then the filter is actually cleared to collect the carbon in various forms. Sometimes it's bottled, sometimes it's in a network, sometimes it becomes a fuel source. But literally the carbon we are absorbing from the atmosphere becomes a commodity, a collected commodity in this scenario that could then be used elsewhere. So our question was, it's great to have these in farms, but can we actually develop a strategy to adopt them in the buildings? Just like the photovoltaics, they used to exist in a farm format. Now they're integrated in many buildings. So we looked at potentially using the building's natural stack effect, where the pressure difference from the bottom to the top of the building will create a natural pull of the air and pull the air through these machines to absorb carbon, so to integrate it with the building systems, in other words, to absorb carbon directly from the atmosphere. And then what could happen here? So it could be carbon absorbed, could be used as, for example, construction material. It could be used as a part of the food and beverage industry. And it could also be used for other things that maybe it's not so intuitive, such as enhanced farming. So there's a broad use that could be adopted if we were to have a good network of carbon in our districts, in our buildings and cities together. And the potential of this, you might ask yourselves, right now it exists in a big farm format. Where is this technology going? So this is actually from a picture from the COP26 conference, and where our Secretary of Energy at the time talked about this particular technology that we must deploy approaches such as emerging direct air capture technology to address issues with difficult to decarbonize industries. So it was particularly highlighted as a potential solution. And since then, we've seen several incentives from the government that's incentivized this type of technologies, their development, and their production, and bringing them to the market as well. And she also said that her agency would invest in research in the nascent field of carbon removal with the goal of pushing the cost under $100 dollars per ton by 2030. So this shows a great commitment from our Secretary of Energy, hence the government. And we are seeing some of the impacts here that this technology is going to keep on maturing very quickly over the next years. And how is this relevant? It is relevant if we compare this to, for example, photovoltaic industry. So you might have seen kind of farms like this on the left side, where photovoltaic fields are created in sunny areas to create energy, to generate energy, or they can be adopted in buildings. So about 15 years ago, the cost of photovoltaics were 90% more expensive. So we saw a 90% cost decrease, and they became quite affordable these days, relatively more affordable. And this is what part of this was, that this was the wide use of the photovoltaics, just like you see on the right side. It's one of our buildings, is the first net zero energy school in New York State, PS 62. As we disperse these technologies, make them available for building scale uses, you can see the cost comes down significantly, uses and implementation also increases too. So we're imagining that with everything aligning, we're going to see similar approaches. From the left side, where these technologies exist in farm format, like you see on the left, can they go to what you see on the right, like our proposals? Can they be building integrated, just like what we see in the photovoltaic scenario? And this really highlights maybe how these three different types of technologies come together in our proposals, from biomaterials as part of the structure, as part of the interior walls and slabs and finishes, how biomass can be created in the facade areas, such as microalgae, and how direct air capture technologies can support that, supplement that, by further actively absorbing carbon from the atmosphere. And wouldn't it be amazing if we could say that every building we create from now on could go to a 350% carbon absorption rather than emission in 60 years? Can we make every building act so? Is a great question. And again, this is just one building, but when we look at it overall, in the broad scale of cities, there is so much more potential. The carbon that we absorb, the algae protein that we create in the building, can of course be used in the building, but also elsewhere. Can we think of a scenario where, for example, some of the carbon that we absorb here and some of the algae we create here goes to building of bioasphalt, biobrick, carbon plastic? Wouldn't that be amazing? Or they can also go to food industry. Or we can extend it to agriculture. Can we enhance the soil? Can we create healthier trees? But can we also enhance agriculture too? And also, maybe more fundamentally, they can go as a, they become a fuel source. Do we need to use fossil fuels going forward? Or can some of this be used as biofuel to clean our fossil fuels, which are the maybe primary contributor to the greenhouse gas emissions globally? And finally, we also think that they can be source of energy. Imagine if the biofuel we create here could be used to generate electricity, or could be used to heat or cool the buildings that we might occupy and the built environment. And if we imagine one step further, can our cities, can our streetscapes also adjust to this new realm? Can we implement some of these strategies in our streets, in our sidewalks, in the spaces that we occupy every day as citizens? And if we do this, this will further reduce our carbon increase our carbon absorption, and so an area that we should not forget about when we talk about built environment holistically. And just to put things in context, so in 1 square kilometer of the city, we can sequester approximately 1,500 tons of CO2 per year. And this could be huge, right? With integration of greenery, intensive planting, but also use of some of these technologies together. And imagine if we were to create a network in a city like New York, for example, or if we were to actually expand this over the globe. Can we create a global network of urban sequoias around the world? And this could save us 1.6 billion tons of carbon each year. And this brings us so much closer to that 1.5 degree that I talked about. And can the built environment be part of the solution here? And in a second, I'm gonna ask Hannah to show the video one more time, so that now that we've maybe heard some of these ideas in more detail, we can look at it more we can see it one more time as a conclusion. But I wanted to emphasize one thing here. We had a great team at SOM, an interdisciplinary team at SOM that was comprised of urban designers, architects, engineers, structural engineers, MEP engineers, sustainability specialists, interior designers, and researchers as well. But also, it wasn't just our work here. We also collaborated with experts in the industry to arrive at some of these ideas and strategies. We work with Architecture 2030, Ed Mazria, Vincent Martinez, and Aaron McDade. We work with University of Colorado, Will Schrubar particularly. We work with Open Air Collective and Chris Needle, their founder. And we work with Pamela Conrad of CMG Landscape Architects as well to develop some of these ideas. Now, Hannah, maybe we can stop here and show the video to end our presentation here. Thank you for that again. I can see that we have a very international audience as well. It's amazing to see all of you participating from different locations. This is wonderful. Thank you for your time. I hope this gives you an idea of how our provocation turned into a prototype. And we try to explore if a building could become like a tree, an absorber rather than emitter, a solution rather than a problem. And I'll maybe finish with an anecdote here before we start with your questions. When during the development of this project, I actually, I thought I have a 6-year-old son who was 5 at the time, and I thought, maybe I should run this idea by my son of that age, see what he might think of this. And it was so interesting that it's so intuitive, maybe, and so not business as usual. When I explained actually that buildings can act like trees and help the climate and help clean the air, he actually looked at me after I said so, and he goes, "Wait, what? Aren't they doing that already?" I mean, it was so intuitive, and it makes me wonder. Yes, why aren't they doing that already, right? It gives me hope that our also next generations are a lot more tuned in and optimistic, and much more proactive in this issue as well. Thank you for your time.
Thank you so much, Yasemin, for that very hopeful and inspiring presentation. It's exciting. I think it's really easy even waking up and reading the news this morning to get down about what's happening in our world right now. And it's just so nice to feel inspired and hopeful about what we can do to help change the future. So thank you for sharing all of this with us. Without further ado, we have a lot of really interesting questions that I'm excited to dive into. So I'm going to try to filter them based on the ones that have the most upvotes right now. And the top question that we have at the moment is from Chuck, who asks, could the inherent stack effect in a tall tower also be used to spin wind turbines for active energy generation?
That's a very good question. And that's something that we were also thinking about too. I think this type of, you're highlighting I'm actually not an engineer who's working in some of these technologies, but as a designer, I think you're right that it's just like any other developing technology, any other nascent technology, we haven't fully explored the broad use, all the uses that this can take, and all the benefits that we can harvest from it. And that's what many scientists, many researchers, and many producers also, product producers, are working across the globe to try to see how some of these systems can be made more effective. Can they be used to create energy in addition to absorb carbon? And I think that there's a whole realm there that you're pointing out something really powerful. There's a whole realm there that is still under exploration, right? And the statement from the Secretary of Energy was a great example that there's a lot more to come here. And we highlighted one technology here, but it's not the only one either. So I say watch this space, and we're going to see a lot more advancement on some of these things. And I suspect they're also going to become a lot more available, a lot more accessible. We're going to see a variety of scales and sizes coming through. And I'm quite optimistic about it, to be honest.
Me too. I feel like even in the past couple of years, there's more and more information available about the expansive thinking that architects are doing and the types of collaborations that they're having with other experts to come up with these new materials and technologies and ways of envisioning the built environment. So I like the scale of your presentation also, to not think about a tree, but to think about the forest and the potential when these technologies are applied on a mass scale. And I like to imagine that kind of a scale. So for the next question, Peter asks, and I'm going to actually tie two questions together because I think that they are their answer might be very similar. So Peter is asking, do the algae panels need to be periodically cleaned like the walls of an aquarium so that they don't get opaque and they don't get an opaque layer of dead algae blocking the sunlight from the interior cells? And then kind of a similarly pragmatic question about the technologies from Breda, who asks, Do these materials have limits in their carbon absorption capabilities as their mass and volume augment with time? So kind of just how will this be dealt with, these types of issues?
Right, and I think just like any other facade system or any other building system, they will require regular maintenance. And what regular means, I think, needs to be, I mean, it's a great example. The solar leaf project, for example, gives a great example of this. And given it's a built example also, there's a lot of data, there's some data available and a lot of articles and research available on that project. So I would encourage actually the groups, the individuals asking the question to look into it in more detail on that project. And you know, just like any other building system, of course, it does require maintenance over its lifetime. It also does have its limit. All of these strategies are going to have their limitations depending on they're going to have their opportunities and limitations depending on the application type, depending on the size of it, the type of it, the scale of it, and the integration, how successfully they could be integrated into the building systems. And you know, it's kind of this holistic approach, again, thinking of them in such a way that every component of the building works for the building, but the building works for the component too. And I think that's kind of the strategy we try to adopt here to enable parts to exist individually, but also become a part of the larger ecosystem to help each other and fully integrate the system, in other words.
Thank you. A more case study kind of a question is Ruju is wondering, he would love to hear more about the building in Hamburg that has algae walls and how you're measuring the impact, and if there's been any new learnings or observations from that particular building. Anything you'd like to share about that case study?
Right. The building is not a building designed by SOM. So I would recommend that. I think those of us who are more interested in getting more information, it was a building engineered by Arab actually, and I would suggest that more information can be obtained from them. And anything I might say, I don't want to misrepresent their research and all the great work that they have done also. So I think this will be more appropriate actually if they can provide a lot more direct and a lot more impactful information to our audience.
That's a great shout out. Thank you. I'm definitely going to be Googling that building also. It wasn't on my radar. So then we have Aman who's asking, wondering about the biofuels that are released back into the CO2 in that releasing CO2 back into the atmosphere in that kind of circular, circular air economy that you were showing the diagrams to. And wonders if the net absorption is greater than the release in that model.
Right. This is a great question, but it's a complicated one too. And it's complicated because, you know, when we did this study, I think there's a couple of, when we talk about kind of global emissions, hence we try to broaden the scale of our effort here from a building to a city, to a district, to a city, and further. Because the impact of, when we talk about, for example, the fossil fuels or biofuels, their impact is not just limited to if and what they emit when they're burned or combusted, right? The other challenge, for example, while biofuels are cleaner than fossil fuels, the other challenge is currently, I don't know if you know this, but we produce biofuel in agricultural fields. So we do actively produce biofuel, actually. So we grow things to become biofuel. And of course, some of it is coming from the excess from the agriculture industry. But what this does is those fields that could be used to grow left alone and could absorb carbon from the atmosphere as natural fields are used as farmlands, for example, to produce some of this biofuel. So I think it's not just the combustion piece, but it's also how can we restore the world's ecosystem in various ways. So we reduce the demand on agricultural fields that are not for human consumption, let's say, by finding alternative source of biofuels. And I think that that's the idea behind some of these biofuel farms that you would see across the globe, and really trying to reduce the global fossil fuel impact, and reduce the global biofuel impact in the lands that we have also. So it's a fairly complex equation there, and I think when we think about biofuels and carbon emissions, we need to look at it more broadly at the whole circularity, carbon circularity, and the whole life cycle of it, and the global impact of it, which might not be immediately, which might not always be immediately in the building or in the built environment, which is really important here. It shows that everything is connected together. All ecosystems has to be considered carefully if you're going to find a solution to our climate challenge.
Yeah, it's a very complex, and it's not as simple as the circular diagram. So thank you for tackling that issue, that question.
I wish it was as easy as this, drawing a circular diagram. Yeah.
And just quickly switching over all economies, but I think that the diagram does do a good job of showing kind of all the different potentials, all the different places that there's potential, which is fantastic. Before I ask the next question, I just want to point everyone down to the icons that are just below the chat box. You'll see a polls icon just below in the lower right-hand corner. If you're interested in knowing a little bit more about Architizer's A+ Awards program, which are launching this October, you can just drop us a line there, select one of the responses, and we can either give you a submission guide or some more information about the program. So just let us know there. And now I'm going to head on to the next question. Dimitra asks for a bit more information about the aggregate that you were speaking about. Does it come from older buildings, or could there be an aggregate produced using older buildings to help reuse them?
Yeah, and there's a lot of research on this. I mean, it's a wonderful question, actually, and part of the approach must always be thinking about circularity of use and reuse of things rather than using virgin materials to begin with, because I'm sure many of us know that it's on this call, but a lot of the emissions coming from the built environment are also part of the, they come from the extraction of materials, crushing of them potentially in this case, then building of them again, transportation of them, heating of them, baking of them. So all of these things add up, and the more we can use the reused materials, recycled materials, obviously a lot of those emissions that we call embodied carbon emissions upfront gets reduced, but also the end of life carbon emissions also get reduced. So, I don't know if all of us are aware, but when we talk about embodied carbon, the whole life carbon cycle, we talk about I like to talk about three categories. Upfront, which is what happens, where the materials come from, how are they extracted, what type of energy is used to create them, to transport them, to build them. And then the second one is the building in use. So the energy that we use, carbon we emit as we operate the building, such as electricity, such as water, such as heating and cooling. And the last piece of it, relevant to this, is the end of life. So we call embodied carbon at the end of life. So a lot of the materials that we want to use to create the circular economy should be used and reused, so that at the end of their lives, we're not sending them to a landfill. Instead, they have a second and a third and a fourth life. They come back to the building industry or other industries to be part of this equation again. So in this kind of ecosystem or equation, there's a lot of, you'll see already in the current existing materials, you'll see that there's a lot of aggregate replacement. You'll see a lot of recycled aggregates used, alternative materials such as glass, for example, coming in as an aggregate to some of the materials. Various forms of crushed aggregates like sand-like materials are coming in. And they're all trying to basically, again, make best use of the recycled content. And they're all trying to minimize the impact that, negative impact that use of virgin materials might have on our environment.
Yeah, I've been reading a bit more about carbon capture concrete as well. And I think that there are so many examples of different companies that are investing money into this type of research. And now we just are waiting to see some of these more available on a wider scale, which is also something I'm hoping is going to become more widespread. And that kind of segues actually to our next question, which is, does SOM have any ideas about how to fund an urban Sequoia like proof of concept project, or some sort of an estimation about the extra cost premium to build a high rise like this today, and the ROI timeline under the current market conditions? That's from Andy.
This is a very detailed question.
Yes.
I mean, obviously we are designers, and we're not, I wish we were in the business of investing into green buildings, but our contribution to it, I think, in the built environment is slightly different. That said, we know we have many clients who are interested in this type of approach, and we know there are many investments, particularly now more than ever. The investment in green technologies, green buildings, and green environment is, I think, it's tenfold from where it was 10 years ago. So there's a huge increase here, and we are seeing a lot of interest in how and what and where. And I suspect this interest is going to grow as more of us think of similar strategies. So I cannot speak to the cost premium, etc. As you know, that's not necessarily as designers something that we perfect, let's say, but we work with various client groups and investment groups to actually explore some of these ideas, and it is very much in the books. And some of these ideas, I believe, are going to go to the next step, and we'll see what they might look like. They might not be this prototype, but the idea here was to create a provocation and a prototype that could change our mindset from accepting buildings as business as usual and they emit greenhouse gases, to make them absorbers and work with like-minded groups, like-minded clients and investors who are also working towards similar goals.
Big fingers crossed. I'm always amazed by architects don't only have to design, and convincing clients also to imagine possibilities that they didn't imagine in the past. People with money to be able to fund these things more and more. I think the past 3 weeks, just hearing people talk about how, oh, the client wasn't thinking this, but we were able to show them the benefits. Also seems, of course, maybe not to do, as you say, like the entire prototype, but to maybe adapt some of these technologies in unexpected ways that we're not seeing right now. So I think we have time for one.
And it might be larger scales too. So I think, you know, who knows? So we'll leave it at that, I think, here.
Yeah. Yeah. I'm going to ask one final question of your time. Thank you. And this is from Himesh, who says, great presentation. What happens to design in this new urban world? Design versus function. Does one have to suffer from the other to prosper? Because from your designs, the buildings would all have similar facades. And I wanted to give you a chance. I think this kind of ties into the way that you just answered the question, the previous question. So I thought it would be a nice compliment.
Yeah, no, that's a great question. To be honest, I don't think, you know, as designers, our jobs is to make sure that we create environments that benefit the health of people, but also health of the planet. And I don't think any of these are challenged or limited by the use, by the program, by the height. And I think our challenge and opportunity as designers is how do we do all of these things with, again, people and a planet in mind. So I do not see them as, I see them as complementary. And, you know, you can imagine that, for example, a residential building will work very different than a potentially a hotel or office building or a retail center, let's say. And the idea would be that we always, as designers, we always try to work with the best, with the pros, with the advantages of that use type, and how can we make the most of it and the benefit from the design integrated adequate strategies to make the best of it. So I would think that going forward also, all use types will prosper. I don't think it's limited to one thing. And as I said, we put out a prototype here, and we chose a particular look that as designers we were appreciating. Doesn't mean that this is the only way it might look. Doesn't mean that this is the only height. Doesn't mean that's the only size either. So I think this is an area that we are continuing to explore at the moment, actually, of different uses, different designs, different facades, different heights. And I think there's a whole exciting world here that we hope that many of you will also join us in this effort to think of the building design and built environment differently, tying it back to the planet and people and our well-being collectively in the globe.
Thank you so much, Yasemin. Thank you for your time. Thank you for answering these questions, for sharing insights with us, and for giving us hope. It's been a really inspiring presentation. And thank you to everyone who came, who joined, and for all of your brilliant questions. I just wanted to mention that tomorrow, myself, my colleague, Paul, who you probably all know, will be back tomorrow at 1 p.m. Eastern Standard Time to wrap up Future Fest with 10 predictions for the future of architecture. And so on the final day of this 3-week-long event, Paul is actually going to be in the presenter stand with one of our friends, Wandile, of the Ubuntu Design Group in the Anti-Racist Hot Dog. They're going to be assessing what comes next for the built environment at every scale, and I hope to see you there at 1 p.m. Eastern Standard Time tomorrow. Thank you again, Yasemin, and thank you to everyone for attending today and for the past 3 weeks. It's been an absolute pleasure.
And thank you, very much appreciated. Great group, great questions. It's been a wonderful discussion. Thank you.
Thank you. Have a great rest of your day.
Bye.
Bye.